Hello students. So we are discussing hydrostatic pressure. In the previous chapters, we discussed pressure exerted by solids, liquids and gases, and also how pressure is transmitted through liquids, and thereafter we discussed the atmospheric pressure, instruments that are used to measure atmospheric pressure, and also the uses of atmospheric pressure. Now I am going to move on to the topic flotation. So when we say flotation, it is related to floating of objects or objects getting immersed in a certain liquid. Normally the liquid that is around us is water. You all know many water bodies. At home we use water. So you have seen so many instances. You all are familiar with certain examples also. Now say when we make lime juice at home. Normally when you squeeze the lime, the seeds go sink in the liquid or the lime juice. Even when you add water, usually it sinks in water. But when you add sugar, when you dissolve sugar, usually you see the seeds floating there. So there you would have observed the concept of floating as well as objects sinking in water or juices. The same way, you all are familiar with swimming. You all know how you float in the swimming pool. When you go into the sea, how things float. So like that, you are familiar with this concept. So what we are trying to understand is how liquids make objects to float, or why objects float in liquids or fluids, or else why do they sink in fluids. So that is the basic concept of flotation. We know that when we put a stone into a vessel containing water, it would sink, while something like a piece of wood would float. So this is what I told you all, even in the beach side, you all might have seen certain objects floating in seawater, some sink in seawater. So here, if you take a stone, if you put it into a vessel containing water, obviously it will sink in water. So if we take a vessel containing water, a stone will sink, whereas a piece of plastic or piece of wood that will float in water. Sometimes you see objects that are partially immersed in water. They are submerged partially, but they are still floating. So you see objects floating or sinking in water or other fluids in different ways. So these are different instances. Let us investigate what scientific principles lie behind the reason for some objects to sink in water while some objects to float in water. So that is what we are trying to understand now. Why some of them float in water, why some of them sink in water, and why some are partially immersed in water while floating. So 3 different instances are shown in the diagram. We will try to understand those. So to do that, we need to understand this concept that is called upthrust. So the word itself gives you an understanding. Up. So there is an upward. Thrust means like a push or a force. So there is a force acting upwards. That is the upthrust, or what we can say as upward thrust. So when we press an object that floats on water, such as a plank of wood on a water surface, we experience a force exerted by the water acting upwards. So this is what happened. Now let's say if there is a container with water, if there is a piece of wood, a plank of wood floating on it, if we try to push it down, when we apply a downward push, you find it, does it go easily inside or is it difficult to push it in? It is usually somewhat difficult, or at least you will experience an upward force. It's difficult to push it down. You can't just easily push it down. Even at home, if you have a bucket of water, if you take a bowl and if you place it on water, the flat side, the bottom side on the surface of water, and if you try to push it down, it's not easy. So that means we experience an upward force. Upward force. So who exerts this upward force, or what exerts that upward force? It is the water. So upward force exerted by water. So that is why we call it upthrust. There is a force that is exerted by the water against an object or against the weight of the object. Now you all can see, if there is an object, the weight of the object will be always downwards. But against the weight of the object, there is an upward force exerted by the water. For that matter, any liquid. So since it is an upward force or an upward thrust, a push upwards, we call it the upthrust. So when we press an object that floats on water, such as a plank of wood on a water surface, we experience a force exerted by the water acting upwards. That's important. Always it is acting upwards. Even for an object that sinks in water, the weight that we feel when it is in water is less than its weight in air. Now even this, you all might have experience. Now you all know people draw water from the well. If you have done it, you will know that. When you draw the water, a bucket full of water, when the bucket is under water, below the water surface, you don't feel the weight that much. But once it comes above the surface of the water, you can feel it being more heavier. It's the same bucket full of water, the weight of the water is the same, but when it is inside water, we don't feel the weight. The reason is the well water is giving an upward push. So that is what we call as upthrust. So for any object, another instance, if we consider another instance, if there is an object partially floating or let's say sunk in water, inside water, immersed in water, or even if it is sinking in water, any situation is the same. Here what will happen is the weight will be acting downwards. Weight will always act downwards. You can show it as weight, or you all know we use the letter W. Then the liquid or the water, the fluid is exerting an upward thrust. So that will always act upwards. So here it's going to be the upthrust. We can use the letter U. Because it's upthrust, upward thrust, we can use the letter U. So usually the weight is downwards, upthrust is upwards. So there. You can see, even for an object that sinks in water, the weight that we feel when it is in water is less than its weight in air. What is the reason for that? Now I showed you all this. Weight is downwards, upthrust is upwards. You are familiar with forces. When more than one forces are acting on an object, what happens there? There will be a resultant force. So weight is acting downwards, upthrust is acting upwards in opposite directions. So there will be a difference. You have to subtract. You know that. When we calculate the resultant, weight minus, we can say, upthrust. So when the upthrust is subtracted from the weight, you see a different weight, or you feel a different weight. We can call that as the apparent weight. That is what I explained you all with drawing water from the well. When the bucket containing water is within the water surface, inside or below the water surface, there is an upthrust acting, there is the real weight, but the weight what we feel is less. Why? Upthrust gets subtracted from the weight. So we feel an apparent weight. So that is what we need to remember. You see an apparent weight. When we use the term apparent weight, something that we feel or something that appears to us, not the real one. There is the real weight and there is the upthrust. Because of that, there is an apparent weight. So that means we feel it lighter than in air. Can you all understand that? So then, so here you can see it is less than its weight in air. This is because water exerts an upward force on objects that are immersed in water. Same thing goes for objects that sink in water also. Even if this object comes to the surface, bottom surface, the same thing. So this upward force is known as upthrust. Not only water, but any fluid exerts an upthrust on objects that are immersed or floating. So here it is a floating object. Here the object is immersed. So that is a floating object. Here the object is immersed. Then there you can have an instance where the object is sinking in water or any fluid. So that is the basic concept of upthrust. Any object has a weight, and when it is either immersed completely, partially, it can be floating, it can sink in the fluid, but still the fluid will exert an upward force, upward thrust. That is what we call as upthrust. Because this upthrust is acting against the direction of the opposite to the direction of the weight when the object is in water is felt less. That is why we call it as apparent weight. So we feel the weight as less than the weight in air. Now we will try to do an activity to understand this concept, that is upthrust. Activity. Demonstrate the upthrust exerted by a fluid. So I explained what upthrust is. An upward force exerted by a fluid on any object that is either floating or immersed partially and floating or sinking in a fluid. Okay. So to do this activity, we need these following materials. First one. Now we need a cube. If it is metal, it's more better because it has more weight. Usually you all know if it's a wooden cube, usually wood tends to float in water. But if we take a metal, it usually sinks in water and it's more heavier. So it's easier to get the reading and understand the changes. Then we need a spring balance. A spring balance. Then we need a container or even a beaker. It can be any glass container, that's fine. And we need water. So we need the cube, a metal cube, piece of metal cube, a spring balance, beaker and water. So this is a simple activity. I will show you all the diagram and explain the method to you. So this is the method. What we will do is, first we will suspend the piece of metal. We will attach it to the spring balance and get the weight of the metal cube in air. So the piece of metal, first we get the weight of metal in air. That is the first instance. Then the second instance. Now you can see this F there. You give a push to the metal downwards. Push the object downwards while it is hanging from the balance. What will you all see? You can imagine. When you all give a downward push, obviously the weight has to increase. So the reading here will increase. Here, of course, students, I'll be doing the activity, but while I explain the method itself, I will explain what happens during the activity. So, when you push it down, obviously you will see the weight increasing. So, the weight of the object is downwards. We give another force downwards. So, the forces get added up. You all are familiar with more than one forces acting on an object. So, the reading increases. Then in this instance, what do we do there? We apply a force upwards. So, that is against the weight of the object. The weight of the object is downwards, force is given upwards. So, what will happen? The reading will decrease. So, you all know two instances. So, first instance, students, we get the weight in air. Then what do? We push it down, observe the reading, push it upwards, observe the reading. Then we will compare these two instances with the result that we get here. What are we going to do here? You take a beaker containing water and you immerse the object into water while you are holding it attached to the spring balance. Then you get the reading. So here you see the apparent weight. What I told you all as apparent weight. Weight that appears to us when the object is immersed in water. Thereafter, you have to observe whether that is equal to the weight of the object in air, or whether it has increased or whether it has decreased. Then you will understand the concept of upthrust. So again, in the next slide also, students, I have the method with the explanation that is given in your textbook. I will read that and explain it to you all. Thereafter, we will do the activity in the lab. So method. Suspend a piece of metal on a spring balance as shown in the figure A. That was the first figure shown to you. And measure its weight. So this is the weight in air. The real weight of the object in air. Now exert a downward force on the piece of metal as shown in figure B. So now we are exerting a downward force. Read the corresponding reading on the spring balance. This is what I explained to you all. It would be seen that the spring balance reading has increased as a downward force has acted. Then exert an upward force on the piece of metal as shown in figure C and read the spring balance reading. It is obvious that the spring balance reading would decrease. So when you exert an upward force, so when it is an upward force, spring balance reading will decrease as an additional force was exerted upwards. This shows clearly that a downward force acting on the object would increase the spring balance reading, while an upward force would decrease the spring balance reading. So as I explained to you all, students, we have the object in air, that would be the weight of the object. When you push it downwards, reading increases. Why? Weight is down, you give a push downwards. But when you push it upwards, what happens? Reading decreases. So I'm sure you all can understand that clearly. So now only we are trying to understand upthrust. Now, immerse the object in water as shown in figure D and read the spring balance reading. So here, object is immersed in water. You will observe that the spring balance reading has decreased. So here also the reading decreases. According to the explanation given regarding the figure C, the spring balance reading decreases when an upward force is acting on the object. So that is what I showed you all here. When we push the object upwards, then only the reading decreases. So when we immerse the object in water also, reading decreases. So that means the water exerts a force upwards. That is why the reading decreases. That's what we are trying to understand here. So two instances, when you push the object up, reading decreases. The same way, when you immerse the object in water also, the reading decreases. So that means the water is exerting a force upwards. That is what you all have to remember, students. So here you can see. Therefore, this confirms that an object immersed in a liquid experiences an upward thrust exerted by the liquid. This is important. So, when an object is immersed in a liquid, or a fluid, it experiences an upward thrust exerted by the liquid. That is what we discussed as upthrust. So, I am sure this is a simple activity and I am sure you would have already understood the concept of upthrust. But we will go to the lab and do this activity now. Okay, students. So, now we are going to do this activity in order to understand that a liquid exerts an upward thrust on an object that is partially or completely immersed in it. So, to do that, I have a jar containing water here. So, here students, I have the Newton balance or the Newton spring balance. You are familiar with this balance. We have the two scales. Both the scales are there. You can see the gram scale on this side. You can see the Newton scale on the other side. So, we can use this spring balance to measure the weight of objects or the force of the exerted onto this spring balance. So, here as I told you all, I have a weight. If I hang it here, you all can see the weight of the object. Can you all see the reading? You can see it is about 230 grams or 2.3 newtons. That is the weight of this object in air. Now, if I push this down, can you all look at the reading? The weight increases. So, that means the force acting downwards increases. So, when I push, I give a force downwards, you can see the total force, the resultant force increases. Now, I will push the object up. I will give a push from the bottom. Now, what can you see? The reading decreases. That is because I exerted a force in the opposite direction. The weight is acting downwards, I exerted a force upwards. So, then there is a decrease in weight. You all can understand that. If we exert a force downwards, the weight increases, the reading increases. When we exert a force upwards, the force decreases. So, that means the reading here decreases. Now, we will see what will happen if we immerse this object in water. Observe the reading closely. Now, I am immersing it. What can you see? Completely immersed in water. What is the reading? When we immerse this in water, what is the reading you all see? It's about 190 grams or 1.9 newtons. Earlier in air, the weight was 2.3 newtons. Now it is 1.9 newtons. So, what is the observation? There is a reduction in weight. So, reduction in weight means what is happening there? There is a force being exerted upwards. From the first two observations, you all know when there is a reduction in weight, that means there is a force acting upwards. So, now here, what is the substance that exerted the force? It is water. So, when you immerse an object partially or completely in a liquid, here it is water, in any liquid, the liquid exerts a force upwards. It exerts an upward thrust. That is what we call as upthrust. So when you immerse an object in a liquid, the liquid exerts an upthrust on that object. So I'm sure you all can understand that concept now. Okay, students. So I showed you all what happens to the weight of the object when we apply a downward push, then an upward push, and also when we immerse it in water. So from that, I'm sure you would have understood the concept of upthrust. But I will write down the observations first. So weight of object increased when a downward push is given and decreased when an upward push is given. Also, that was one. Then we compared that. The weight decreased when the object was immersed in here. Of course, students, we are not going to do any calculations, so don't worry about the values. You need to understand the concept. The weight of object in air, it was 2.5 Newton. But when we immersed it in water, it was 1.9 Newton. So what happened there? The weight looked less than the weight in air, or it appeared to be lighter than in air. That is what I called as apparent weight. So apparent weight is lesser than the real weight. Why? Because water exerts an upward thrust. So that is the conclusion that we can get from this activity. So if we write down the conclusion, the weight of object is less when immersed in water because water exerts an upward thrust. This is known as upthrust. So now I'm sure you all can understand that concept. So let's try to confirm it again. Now we have a container. Then we have an object. We have the object in air also. So when the object is in air, it has a weight. But when it is immersed in water, the weight is acting downwards and the upward thrust is acting upwards. So because of that, we see an apparent weight. And you all have to remember, students, the apparent weight will be equal to, from the forces, resultant of forces, you all know, the real weight minus upthrust. Or you can say the weight in air, or the real weight of the object. So this is going to be in newtons, because these are all forces. Upward thrust is also a force. So upthrust will have the unit force. Is that clear to you all? I am sure you all can understand that. So with that, I will move on to the next slide. Then here again, we have an activity where we are trying to measure the upthrust. Activity measuring the upthrust. For that also, we need certain materials. These are the materials. Now, this is a jar that is available in the lab. It is either made up of metal or it's made up of plastic. So, this is known as a displacement jar. Or it's called Eureka jar. Or Eureka cup, displacement jar, any term can be used. The name Eureka means victory. It's actually Archimedes, a great philosopher. He was the one who came up with this, or he is the one who explained this concept of upthrust. So when he identified that, when he realized that, he was actually screaming Eureka. So that's why the displacement jar is also called as Eureka jar. I'm sure you all would have heard of that story before. So we need a displacement jar or an Eureka jar. Then we need a spring balance. And also we need a metal object. So it can be a cube. Now in our activity in the lab, instead of using a metal cube, what I will do is I will use a set of weights. Then it's easy for me to identify the middle mark and show you all the activity clear. So these are the materials that we need: a displacement jar or Eureka jar. Then we need a spring balance, and also we need a metal object or piece of metal cube. Anything is fine. So this is what we are going to do. This is the method. First I'll explain the diagram, then we'll go and read the method. So here you can see, initially there is the Eureka jar. In addition to that, we need a beak also. So I will include that with the materials. In addition to this, we need a beaker, as well as we need an electronic balance. Electronic balance or even a table balance. The chemical balance that is available in the lab, we can use any one of those. So there, first we have this displacement jar. We fill water into it. When you fill water into it, it will come up to this level. Even if you pour additional water, that will flow out. So always there will be water up to this mark. This is the water outlet. Excess water will flow out through that. So we need to fill water like that first, and then we need to discard that water. We need to have an empty beaker here. So thereafter what we do is we take this piece of metal block and we need to mark the half the volume. Now here you can see this is the full volume. We have marked the line there at the half volume level. So you can put a rubber band there to mark that value. So as I told you all, since I will be using a set of weights, I'll be using 4 weights. So the 2 weights will be the half mark. So it's easy to identify the mark there. Then that is the first instance where you have attached the object to the spring balance, but it is above the water level or just above the water level. So it is not immersed in water, it's still in air. Then you get the weight of the object, that is the reading of the spring balance. So here we get the weight of the object. At the same time, you measure the weight of this beaker. So, we take the weight of object as well as weight of beaker. The first instance is it's near the surface of water. Then the second instance, can you all see? We immerse the object to the half volume mark, where you put the rubber band or where it the half volume mark. You immerse it into water. You all are familiar with this also. At home, when you fill the bucket with water, completely fill it up to the brim, and then if you put an object into it, obviously the water flows out. The same thing happens here. When you immerse the object in, the water flows out. That is what we collect in this small beaker. There, what you need to do is, while it is immersed half volume in water, you need to get the spring balance reading, and also you need to get the weight of the beaker with displaced water. Now, when water flows out, we say it as displaced water. It's displaced by the object. The object only pushes the water out, or it displaces the water out. So, this is the displaced water. So, here beaker with displaced water. So, we get the weight of that. Then third instance, you can see here completely the object is below the water surface, completely immersed. This we call it as partially submerged. This is completely submerged or completely immersed in water. So, there you can see there will be more water displaced. So, again we get the Newton balance reading as well as we get the weight of the beaker containing water. Always we need to take 2 readings. Then the last instance, we immerse the object further into water. We don't touch it on the surface. We don't rest it on the bottom surface. It's below the surface of water, somewhere in the middle. There you will see there will be no additional water flowing out. In this instance, you saw water flowing out. Here also we see water flowing out. Here there is no change. But to confirm it, we need to get the reading of the Newton balance as well as the water with the beaker. So, always we take 2 readings, and we need to take readings under these 4 instances. Is that clear to you? Then we will do the calculation and try to understand the upthrust exerted by the water, or we will calculate the upthrust exerted by water. So, there. The method, get a cubic shaped piece of metal and mark by a line where its volume is divided into 2 equal parts. That's very important. Volume is divided into 2 equal parts. Now, hang it on a spring balance and measure its weight in air. Get a beaker and measure its weight. That is the first instance. Now, submerge the metal cube in water to each of the levels indicated by the figures A, B, C and D, and record the spring balance readings and the weight of the beaker together with the displaced water each time. So, that is what you need to do here. You take the weight of the object in air, then the beaker alone. Again, 4 different instances. Here also I explained to you all, it's same as having the object in air and the beaker alone, because you can see there's no water displayed. So, those are the readings that we need to take, and then we will try to understand the upthrust exerted by water. So, it's a simple activity, students. We will go to the lab and do the activity now. Okay, students. So, from the previous activity, you all understood that all the liquids exerted upward thrust, the upthrust on an object immersed partially or completely in a liquid. So, here as the liquid we use water. So, water exerts an upthrust on the object. So here in this activity, I am trying to understand or demonstrate the relationship between the weight of the object when it is immersed partially or completely in water, and when we are immersing the object, there is a certain amount of water that will be displaced. So we will be collecting that water in another beaker and we will get the weight of that water that was displaced. And thereafter, we will try to find the relationship between the upthrust, the weight of the water displaced, as well as you all know when we immerse the object in water, there is a reduction in weight. That also you all observed in the previous activity. So the reduction in weight. So there are three components: the reduction in weight, the upthrust, and the weight of the water displaced. We will try to understand the relationship between all three components. So to do that activity, I have slightly modified the activity here. Without holding the object and immersing it, I am going to use a stand so that I can easily hang the object to the particular point. So here these are the 4 stages in which we need to get the reading. So initially the object, now this is going to be the object. This is a set of balance, students. You all can see that there are 4 weights. So half volume is going to be 2 weights. Full volume is going to be all 4 weights. So then it's easy for me to immerse it into the water as well. So initially the weight or the object has to be near the water surface. We need to take the reading of the spring balance as well as the weight of the beaker with water. Then the object has to be half submerged. Third instance where the object is completely submerged, and finally we need to have the object completely submerged but more into water. In the third instance, the object will be completely submerged but closer to the surface of water. In the fourth instance, it will be into water. So those are the 4 stages we will get the readings. So to start the activity, first I need to fill this jar. You all know this is a displacement jar. So in this, when we fill water, it will come to a certain level. Thereafter, after this point, the excess water will flow out. So that is what I am going to do now. I am going to add water. The excess water will flow out. So we will need to allow it for some time until all the water flows out. At the same time, students, what I am going to do is I am going to use the stable balance to measure the weight of the beaker containing water. It's 0. So we will place it here, and now you all can see the reading. 30 grams, so that means it is 0.3 Newton. So initially when we bring the object closer to the surface of water, there will be no water displaced from the displacement jar. So the reading of the beaker will be 0.3 newtons. At the same time, I will get the weight of the object. So here we will hang it. You all can see clearly, students, it's 4 Newton. So the weight of the object is 4 Newton. Weight of the beaker is 30 grams. So it's 0.3 Newton. Right. So now I'm going to first hang the Newton balance here. And then I will hang the weight. So here I have actually set it to a level where it is going to be near the surface of water. So that is in the middle, it's near the surface of water. It's not immersed, it's near the surface. So now I am going to remove this beaker. I will set the second beaker. Now we need to set it up so that now I have the beaker. So the displaced water will be collected inside the beaker. You can get the weight of the beaker with water in this. And initially you all can see, I will adjust it so that it becomes more closer to the water surface. So now the object is closer to the surface or near the surface. So students, now this is the first stage. The object is near the surface of water. Can you all see the Newton balance reading? It's 4 newtons. And also you all can see the beaker, there's no water displaced. The beaker alone, the weight is 30 grams. So it's 0.3 newtons. That is what I have to fill in here. This is 4 newton and that is 0.3 newton. Okay students, so now I have to half submerge it in water. Now here it is half submerged. So you can see here students, the water has been displaced. At this time we need to look at the reading of the Newton balance as well as the reading of the beaker containing water. So can you all see the reading here students? It's 3.7 newtons there. So then at the same time you have to get the reading from here as well. It's 60 grams, so that means it is 0.6 newton. So that is what I will have to note down here. 3.7 newton for the spring balance with the object hanging from it, and this is 0.6 newton. So then what do? We need to completely immerse the object in water, but it has to be near the surface, near the water surface. So that is what I am going to do next. Now can you all see? It's completely immersed. Again you need to get the reading. So here also you need to get the reading of the Newton balance as well as the beaker containing water. Look at them carefully. So here you can see students the Newton balance reading. It is 3.4 newtons. At the same time, if we get the weight of the beaker with water, it's 90 grams. So it's 0.9 newtons. That is what I need to enter here. 3.4 newtons and this is 0.9 newton. So now what do? We need to immerse the object further down into water, but it should not touch the bottom surface of the container. So what I will do is, I will immerse it further, but it is not touching the surface. Here you can see the reading students, reading of the Newton balance. It's 3.4 newtons. The same reading as before. And also the beaker containing water, that is also 90 grams. So that means that is 0.9 newtons. Is there a change? No. There is no change when the object is completely immersed in water. So if I write the reading here, that is again 3.4 newton and 0.9 newton. So those are the readings that we have obtained. So initially I had the object where it was near the surface, it was not immersed in water, and before that I got the reading when just in air. So the weight of the object, it was 4 newtons. At the same time, the beaker was 30 grams, so the weight of the beaker is 0.3 newtons. the same values were obtained when the object was near the surface, not immersed, near the surface. So again, the weight of the object was 4 Newton and the beaker with displaced water, it was just 0.3 Newtons. Then when we half submerged the object, you saw the reading decrease here, it became 3.7 and the beaker with water became 0.6 Newtons. When completely immersed and near the surface, the reading of the object became 3.4. At the same time, the beaker containing water became 0.9. When you further immerse it below, away from the surface of water, still the readings remain the same. 3.4, the weight of the object, that is the Newton balance reading, and 0.9, the beaker containing water. So from these, what can you all see, students? You can see initially the weight of object in air 4 Newton. But as we immerse it, partially immersed or half submerged, the weight decreased. Completely submerged also, the weight decreased. What is the reason? We understood that there is the upthrust acting upwards. Due to this upthrust, there is a reduction in weight. So that is the weight what we see when we immerse an object in water or for that matter liquid. So when an object is immersed in a liquid, there is an apparent weight. That means there is a weight loss. So we need to calculate the weight loss. So we have the beaker with displaced water. There you can calculate the weight of water. Then we can find the relationship between the loss of weight, the weight of water displaced, as well as the upthrust. So that is what we are going to establish using these values. Okay, students. So you all saw the activity. I am sure you all understood what happened and you can remember I wrote down all the values there. All 4 instances, the reading of the spring balance as well as the weight of the beaker with or without water. So those are the values that we need to fill into this table. So here you can see the table is given in your textbook also. The first column is the stage, the 4 different stages. Metal cube near the water surface, then B, metal cube half submerged in water, that is the half volume mark, and then C, metal cube fully immersed in water and near the water surface. Then the last instance, cube fully immersed in water and far from the water surface. So there you saw what happened. We need to write down the spring balance reading and weight of the beaker with displaced water. Both have the unit Newton. Spring balance reading is also Newton, weight is also Newton. You all can remember, students, the weight was in grams, but I told you all in Newtons. So those are the values that I am going to write down as observations. So when it was near the water surface, you saw the spring balance reading as 4 Newton and weight of the beaker with displaced water was 0.3 Newtons. Thereafter, when it was half submerged, this became 3.7 Newton and this became 0.6 Newtons. When it was fully immersed in water and near the water surface, there again you saw the reading becoming 3.4 Newton and 0.9 Newton. Then the last instance, cube fully immersed in water and far from the water surface, that also had the same reading 3.4 Newtons and 0.9 Newtons. Those were the observations that we got. So now we will try to understand these observations. Initially, students, you all can remember, although we say 4 instances, the object in air, that is also 4 Newton. Then when the object was just near the water surface, still this is water. Instance A, there also this is 4 Newton. But when it was partially immersed, that is half immersed or half submerged, metal cube half submerged in water, then you saw the reading as 3.7 Newton. When it was completely submerged, so there it became 3.4 Newtons. So at the same time, when it was in air, it was only the beaker. Beaker, the weight was 0.3 Newtons. Whereas when it was here also, the same weight, 0.3 Newton. There was no water displaced. But in this instant, you saw that there was water displaced. What is the weight of the water displaced? Beaker is 0.3. With water, it's 0.6. So, what is the difference? 0.6 minus 0.3. That is again 0.3 Newton of water that was displaced. Can you all see a relationship there? Now here it's 4 Newton, only the object. Now here the weight of the object has become 3.7 Newton. At the same time, 0.3 Newton of water has been displaced. So can you all see a relationship there? This is the apparent weight. This is the weight of water displaced. When you add them together, you get the weight of the object in air. 3.7 and 0.3. You get the weight of the object 4 Newton. The same way, the last instance, what happened? Or the third instance actually. What happened there? The weight became 3.4 Newton and the weight of water 0.9 minus, we need to subtract from the initial value, only the beaker. So 0.9 minus 0.3. That is equal to 0.6 Newton of water. So there again you can see 3.4, 0.6. When you add them together, you get the value 4 Newton. When you push the object further down, cube fully immersed in water and far from the water surface, there is no change. So only when it is half submerged, there is a certain amount of water displaced. Completely submerged, there is a certain amount of water displaced, but it doesn't depend on the position of the object underwater unless it goes and sinks in water. There, of course, there's a different instance. So here we looked at 4 different instances. So these are the calculations. We will use these values and fill the table that is given in the next slide. So what conclusions can you draw from the above activity? So to come to the conclusion, students, as I showed you all before, we need to do the calculation as well. So, and we need to fill this table. The stages, again the same 4 stages are given to you. Metal cube near the water surface, metal cube half submerged in water, metal cube fully immersed in water and near the water surface, and the 4th stage or D, cube fully immersed in water and far from the water surface. So there we did the calculations. I showed you all the calculation where we calculated the weight of water that was displaced. You all can remember that. So weight of water that was displaced, weight of displaced volume of water, that is 1, and we need to find the upthrust. Now earlier I showed you all these students, again the same thing. We have the object. When it is immersed in water, this is water, weight is acting downwards, upthrust is acting upwards, and we see the apparent weight. Apparent weight is what? Weight minus upthrust. So here this is water. So I told you all apparent weight is equal to weight minus upthrust. So what is upthrust? if you rearrange the equation, you will see weight minus apparent weight is upthrust. Weight minus apparent weight. Is that clear to you? Because when you subtract the upthrust from weight, you get the apparent weight. But if you subtract the apparent weight from the real weight, you get the upthrust. What is the reason? We see the apparent weight because the upthrust is acting upwards. So, to get the upthrust, we take the difference between the weight in air or the real weight and the apparent weight. So, that is what we need to fill in the first column. Just to show you all the values, I'll go back to the previous slide. You can see there, students, initially in air it was 4 Newton, then 3.7, 3.4 and 3.4. So, if we calculate the upthrust. So, for the first instance, metal cube near the water surface, you all can remember, students, the weight in air is 4 Newton. Near the water surface also it is 4 Newton. So, is there an upthrust? No. So, here the values are 4 minus 4, that is equal to 0. Upthrust is 0. At the same time, if we look at the instance where metal cube is half submerged in water, the weight was 3.7 Newton. So, 4 minus 3.7, that is equal to 0.3 Newton. Metal cube fully immersed in water and near the water surface. So, there what happened? 4 minus 3.4. That was equal to 0.6. You don't really have to write Newton, although I have written it here because it's given with the heading. Then again, cube fully immersed in water and far from the water surface, it remained the same, 4 minus 3.4. So, that is also 0.6 Newton. Now, can you all see? When it is near the water surface, there is no upthrust. That is why upthrust is 0. The weight is same as the weight in air. Then when you immerse it partially or half submerged, the upthrust is 0.3 Newton. When you fully submerge it, it's 0.6. So, half submerged and fully submerged, you can see the upthrust becoming double, 0.3 and 0.6. But even when it is fully submerged, even though you push it further down, far away from the surface, there is no change in the upthrust. It's the same value, 0.6 and 0.6. Then we calculated the weight of displaced volume of water, that also in Newtons. So again, I will go back and show you all the readings. You can see there, the beaker alone was 0.3 Newtons. So I told you all here. Then there was no water displaced. So the weight of water is 0. Thereafter we calculated it at 0.3 and 0.6 Newton. So there, initially weight of water displaced was 0. Then it was 0.3 Newtons, 0.6 Newtons and 0.6 Newtons. Now can you all see the relationship? When it is near the water surface, upthrust is 0, weight of water displaced is also 0. When it is half submerged, upthrust is 0.3, weight of water displaced is also 0.3. When it is fully submerged, upthrust is 0.6, weight of water displaced is also 0.6. Even when you push it further down, the upthrust or the weight of water does not change. It's the same thing, 0.6 and 0.6. So, from this, what can you understand? Whatever the instance is, the upthrust is equal to weight of water displaced. Is that clear to you? And also, when it is half submerged and fully immersed in water, you can see the upthrust becoming double. But when you push it further down, there is no change in the upthrust. So that is a relationship. The upthrust exerted by water or any fluid for that matter is equal to the weight of water that is displaced by the object when you immerse it in water. I will explain that in the next slide. So here, students. So here initially we had the object in air, only the weight in air. Then what did we do? We partially immersed it in water. So their upthrust equal weight of water displaced that was equal to 0.3 Newton. Then we had the last instance. Here also upthrust equals weight of water displaced but that was equal to 0.6 Newton. So from all these, the last instance also, when you push the object further down, immerse it further down, far away from the surface, still the upthrust and the weight of water displaced are same. So from this, we can conclude and say the upthrust exerted by a fluid. So here of course it's water is equal to the weight of the fluid displaced by the object. That is one conclusion that you can understand. So when another one, upthrust when fully submerged is equal to upthrust when half submerged into 2. Initially it was 0.3, then it became 0.6. Then also we got these relationships. What did we see? There is the weight in air or the real weight that is equal to upthrust plus apparent weight. So why do we get an apparent weight? Because the upthrust causes a weight loss. That's why the apparent weight is always less than the real weight. So that is another thing you need to remember. Students, these are not laws or principles. These are what you observe and what you need to remember. The points that you need to remember. So there is the weight of the object in air that is equal to upthrust plus the apparent weight. So apparent weight is always less than the weight, real weight. So apparent weight is always less than the real weight or weight in air. So the real weight or weight in air is always greater than the apparent weight when the object is partially or fully submerged in a fluid. Is that clear to you? So this upthrust causes a weight loss, or it decreases the weight of an object. That is why we feel it lighter when an object is inside a fluid or within water. Can you all understand that? So these are the things that you need to remember. So if I go back, this is what we understood. Weight of object in air, then we saw the upthrust was equal to weight of water displaced, partially immersed, then fully immersed. Again upthrust was equal to weight of water displaced. So from those, we were able to come to this conclusion. The upthrust exerted by a fluid, that is water in this instance, is equal to the weight of the fluid displaced by the object. And also upthrust when fully submerged is equal to the upthrust when it was half submerged into 2. And these are the points, as I told you, you need to remember. Weight in air is equal to upthrust plus the apparent weight, that is the weight that you see due to the upthrust, the decreased weight. And then apparent weight is always less than the real weight or weight in air. Here, if you want, you can also mention, that is when the object is partially or completely submerged in a fluid. So I told you all before, students, when we were looking at the materials needed, when I showed you all the displacement jar or the Eureka jar. So I told you all Archimedes. He is the one who explained this concept. So from these conclusions, what I told you all as the upthrust is equal to weight of the fluid displaced by the object, that has been proposed by Archimedes, and that is known as the Archimedes principle. So with that, I will end this chapter. In the next chapter, I will start with the Archimedes principle and we will discuss some more observations thereafter.